Good morning, all of you. Welcome to Jayendra Hank Zone. Now we are in the last lecture of states of matter. So that is liquid state. Now we are going to discuss. Listen carefully. So coming to liquid state, we have completed already Van der Waals gas equation and ideal gas equation. Last topic in this chapter is liquid state. So that we are going to discuss. It's only a few. It's a small topic. After that, we'll do summary of the chapter. Then this states of matter will be completed. So surface tension. First topic in this liquid state is surface tension. Surface tension of a liquid is defined as a force acting at right angles. Important statement here is the force acting at right angles to the surface along a length of 1 centimeter of the surface is called surface tension. Surface tension is represented by Greek letter gamma. It is represented by letter gamma. This is the Greek letter gamma. Owing to surface tension, molecules tend to leave the surface, that is, the surface of the liquid tends to contract to the smallest possible area for a given volume of the liquid. So here, the molecules tend to leave the surface, that is, the surface of the liquid tends to contract the smallest possible area for the given volume of the liquid. Further, for a given volume of a liquid, a sphere has the minimum surface area, which explains why drops of liquid are spherical. Why the drops of liquid are spherical? Because they occupy the minimum surface area. Hence, it is apparent that surface tension. So it is apparent in order to increase its surface area, force must be exerted to overcome the surface tension. What must be exerted? To overcome the surface tension, a force must be exerted to overcome the surface tension. In other words, work has to be done to increase the surface area, and the surface area of the liquid is defined as the surface tension of a liquid. So surface tension of a liquid is defined as the work done, that is work energy required to work energy required to expand the surface of a liquid by unit area. Mathematically, surface tension is equal to work done by change in area. So therefore, the surface tension of a liquid may also be defined as the force in dynes necessary to rupture its surface along a length of 1 centimeter. That is force acting per unit area. It is called surface tension. It is other alternate to pressure. So in SI unit, surface tension is defined as a force in SI units. Surface tension is defined as a force in Newton required to rupture a length of 1 meter of surface of a liquid. Hence, the units of surface tension is dynes per centimeter as per CGS system and Newton per meter it is SI system. It is just related to pressure. Pressure is equal to what? Force by area. So here it is nothing but force by length. Force by length. This is called surface tension. Surface tension is equal to force by length. So Newton per meter. So this is called surface tension. Now variation with temperature. What happens with the temperature? The surface tension of a liquid decreases. Very important point because they'll ask this in the competitive exams. As the temperature increases, the surface tension of a liquid decreases with the increase of temperature and becomes zero at its critical temperature, where the surface of separation between the liquid and its vapor disappears. The decrease in surface tension with an increase of temperature is due to the fact that with an increase of temperature, the kinetic energy of the gas molecules increases and hence the intermolecular force of attraction decreases. As the intermolecular force of attraction decreases, surface tension also decreases. So this is called the variation of temperature, surface tension with respect to temperature. What is the statement now? The surface tension of a liquid decreases with an increase of temperature and becomes zero at its critical temperature. So surface tension is becoming zero at its critical temperature. What is critical temperature? The temperature at which a gas can be liquefied. The temperature above which a gas cannot be liquefied is called its critical temperature. So the surface tension of a liquid decreases with an increase of temperature and becomes zero. This is also important here. So becomes zero at its critical temperature where the surface tension of separation between the liquid and its vapor disappears. So the decrease in surface tension with an increase of temperature is due to the fact that with an increase of temperature, the kinetic energy of the gas molecules are the kinetic speeds, hence the speed of molecules increases, and hence the intermolecular force of attraction decreases. So surface tension is proportional to pressure, you can see simply. So as the pressure increases, surface tension also increases, and the force of attraction decreases with respect to increase of kinetic energy of the molecule. Next case in this chapter is, in this topic, is viscosity of gases. Viscosity. What is viscosity? Viscosity is defined as the internal resistance, that is opposition offered, internal resistance that one part of a fluid offers to the flow of another part of the fluid. This is called viscosity. It is a resistance, internal resistance offered by one part of a fluid to the another part of a fluid. Fluid is nothing but gases or liquids. Similar to liquids, gases also show viscous behavior. For example, for gases, we generally assume planes at a distance of mean free path. The coefficient of viscosity neta, this n is called coefficient of viscosity, is given by expression neta is equal to 5 by 16 sigma square m into kt, where k is called Boltzmann constant, t is called temperature, and pi is called constant, whole to power 1 by t, where k is the Boltzmann constant equal to r by n naught, and n and m are diameter and mass of the molecule respectively. N and m are mass of the molecule respectively, diameter and mass of the molecule respectively. So reciprocal of n gives fluidity. So the variation of sigma with the pressure and temperature gives the nature of the intermolecular forces in the gases. Again, I repeat the statement. The variation of sigma with pressure and temperature gives the nature of the intermolecular forces in the gases. So the unit of viscosity is poise, that is dynes per centimeter square in Celsius, and Pascal, that is Pascal second, dynes, and this is Pascal second. What is poise means dynes per centimeter square and second, dynes and dynes second per centimeter square, and Pascal second, that is Newton's second per square meter. Newton second per square meter in SI units. So poise and Pascal second. Poise second and Pascal second. What is poise means? Dyne second centimeter square. So viscosity, this poise is also important. So please note down in your class for what is poise. Poise is the unit for viscosity. In CJ system, it is nothing but dyne second centimeter square per centimeter square. Dyne second per centimeter square is the, it is nothing but together it is called as poise. And Pascal second is the SI unit of viscosity. Viscosity of gases, like unlike for liquids, increases with the increasing temperature and is independent of pressure. Very, very important. Viscosity increases with the increase of temperature, and it is independent of pressure. I hope it is clear. So this is called viscosity of gases. Viscosity of gases is defined as the internal resistance that one part of a fluid offers to the flow of another part of the fluid. So this is called viscosity. So variation of viscosity and surface tension, they will ask for competitive exams, entrance exams. So what is the variation of viscosity with temperature? Viscosity increases with the increase of temperature. Viscosity increases with an increase in temperature, and it is independent of pressure. And what is the variation of temperature with respect to surface tension? Surface tension decreases. Surface tension of a liquid decreases with an increase of temperature and becomes zero at its critical temperature. And surface tension increases with the increase of pressure also. And whereas viscosity is independent of pressure. So this is clear. So this is called viscosity and surface tension of gases and liquids. Next, next important topic in this uh, next important topic is vapor pressure. So the movement of molecules from the liquid phase into a gaseous phase, evaporation, goes on continuously. If the surface over the liquid phase appears in the vapor phase, return after collision with the covered area and thus strike the liquid surface and stick here. So like this, here the ethanol initial. So this is called liquid phase. And furthermore, then as the number of gas phase molecules increases, the probability increases that a molecule in the gas phase will strike the liquid surface and stick there. This phenomenon is known as condensation. So first case it is evaporation, second case it is called condensation. So the rate of evaporation remains constant with the time, whereas the rate of condensation increases with the time. So eventually the two attain the two will become equilibrium. The two will attain equilibrium. That is rate of forward action is equal to rate of backward action. So the number of molecules returning to the liquid exactly equals the number of molecules escaping from it. Then this is called equilibrium condition. If the number of molecules returning to the liquid exactly equals the number of molecules escaping from it, then the number of molecules in gas phase attains a steady value and the pressure of the vapors at this stage becomes constant and is usually referred as vapor pressure. So this is called vapor pressure. So more about vapor pressure we'll discuss in dilute solution. Simple words I'll tell you what is vapor pressure because if you it's very difficult to remember all these words. So in simple words I'll tell you what is vapor pressure. If the rate of evaporation of gas molecules is at equilibrium with the rate of condensation, rate of condensation. Whatever the pressure develops at this position, the pressure at this position is called, at this position is called vapor pressure. So simple words I'll tell you. So if the rate of evaporation of the gas molecules is equal to rate of condensation, is in equilibrium with the rate of condensation of liquid molecules. Liquid molecules will be for condensation, gas molecules will be for evaporation. So if the rate of evaporation of gas molecules is equal to rate of condensation of liquid molecules, the pressure at this position is called as vapor pressure. So then we can say evaporation is in equilibrium with condensation. When evaporation is in equilibrium with condensation, that is the rate of escaping of gas molecules from the surface of the liquid is equal to the rate of escaping condensing of the liquid molecules into the liquid is called as vapor pressure. So at the position of vapor, rate of evaporation is equal to when the rate of evaporation is equal to rate of condensation. So rate of evaporation will be for gas molecules and rate of condensation will be for the liquid molecules. The pressure developed at this position is called vapor pressure of the liquid. This is called vapor pressure of the liquid. So ethanol, if you take in initial condition, then when if you heat the temperature, what happens ethanol? Some molecules of ethanol will change into gas molecules. Ethanol liquid change into ethanol vapors. So the rate of evaporation, if it is equal to rate of condensation, that is the number of molecules in the gas phase, if the number of molecules returning to the liquid exactly equals the number of molecules escaping from it, it is called as equilibrium position. So the pressure at this equilibrium position is called vapor pressure. So this position is called, this height is called as vapor pressure. I hope it is clear. So this is called vapor pressure. So in simple words, for a liquid, if the rate of evaporation is equal to rate of condensation, the pressure at this moment is called as, at this position is called as vapor pressure. Simple. So rate of evaporation is equal to rate of incandescence. Means what? If the rate of evaporation of a gas molecule is in equilibrium with the rate of evaporation of the rate of condensation of the liquid molecule, we can say, yeah, at this position, whatever the pressure is developed, it is called as vapor pressure of the liquid. So the number of molecules returning to the liquid exactly equals the number of molecules escaping from it is called vapor pressure. It is called as vapor pressure. Next continuation. So third topic in liquid studies, we have vapor pressure. So continuation of vapor pressure. Nature of liquids. Factor stepping. Liquids have different magnitudes of intermolecular attractive forces and therefore have different vapor pressures. Liquids with higher intermolecular attractive forces. Very important point. Liquids with higher intermolecular attractive forces have lesser tendency for evaporation and thereby possess low vapor pressure. And as the temperature of a liquid increases, the molecules move energetically and therefore escape more readily from their neighbors. Hence, vapor pressure of every liquid increases as the temperature increases. And that is given by the equation 2.303 log of P2 by P1 is equal to delta H, that is heat of the reaction by R into T2 minus T1 by T1 T2. This is where delta H is called heat of vaporization. So, as the temperature increases, vapor pressure also increases, and liquids with high intermolecular attractive forces have lesser tendency for evaporation, so they have low vapor pressure. So liquids with higher intermolecular attractive forces have low vapor pressures, and as the temperature of a liquid increases, the molecules move energetically and can therefore escape more readily from their neighbors. Hence, vapor pressure of every liquid increases as the temperature increases. So this is a variation of temperature and nature of liquids. That is the factors affecting vapor pressure. Factors affecting what? Vapor pressure. Continuation now. So with this we are completed. That is liquid state. Now we are going to discuss summary of the chapter. So in liquid state, what we have only 4 topics. That is first one we have. So in liquids we have first one, surface tension, and second point we have viscosity, and third point we have vapor pressure and factors affecting them. So surface tension, what happens with the increase of temperature? Surface tension decreases. Viscosity, with the increase of temperature, surface tension also viscosity also increases, and it is independent of pressure. Very important point is it is independent of pressure. And vapor pressure, liquids with more intermolecular attraction, depends upon nature of liquids. Liquids with more intermolecular attraction has less vapor pressure. Intermolecular attraction has less vapor pressure. And second point, with the increase of temperature, vapor pressure of a liquid also increases. Vapor pressure of a liquid also increases. So this is a summary of this topic only, that is uh, liquid state. So liquid state, surface tension of a liquid, viscosity of a liquid, vapor pressure of a liquid. So all the 3 points they may ask in the entrance examination, but usually you'll get more questions from gaseous state only. So this viscosity, vapor pressure, and surface tension. What is vapor pressure? When the rate of evaporation is equal to rate of condensation, the pressure developed at this position is called as vapor pressure of the liquid. The pressure developed at this position is called vapor pressure of the liquid. What is viscosity and what is surface tension? We already discussed. So this is the end of the states of matter chapter. Now we are going to discuss the summary of the chapter, what you are supposed to do for entrance exam. So summary of the chapter now we are going to discuss. So let us start summary of the chapter. So please concentrate on the summary of the chapter and whatever we have discussed. So work out more questions on those topics only. 100% you can achieve success in the entrance exams. So summary of the chapter. First we have done gas laws. That is what we have: Boyle's law, Charles' law, Avogadro's law, next we have gas equation, ideal gas equation, that is called ideal gas equation. Ideal gas equation. After ideal gas equation, what we have? Dalton's law of partial pressures, Dalton's law. And finally we have Graham's law of diffusion. Graham's law of diffusion. Graham's law of diffusion. Second topic in this chapter we have kinetic theory of gases. Kinetic theory of gases and the molecular speeds. and the molecular speeds. Third topic we have kind of theory of gas and molecular speeds. Third topic we have real gas, ideal gas, Van der Waals equation. Ideal gas, comma, real gases, Van der Waals equation, Van der Waals correction, comma, critical phenomena. Critical phenomenon. And fourth topic we have simple, it is nothing but liquid state. So in all this we have done many numericals and many important models. In ideal gas equation, the one which I am underlining, please note down, do questions more on this. Dalton's law, Gram's law of diffusion. These three are very important. And from Boyle's law and Charles' law, so just writing from Boyle's law and Charles' law, Charles' law, graphs are important. Graphs are important. So please go to the graphs from Boyle's law and Charles' law. So first area is completed. So do more questions on ideal gas equation, Dalton's law, Graham's law of diffusion. And second, we have kinetic theory of gases and molecular speeds. This is also the important area. So you have to work out, as we have done many models in this also. So whatever the models I have done, so please do that questions more and more from entrance books. Easily you can understand this concept and easily you can get success. And third one is most important because ideal gas, real gases, Van der Waals correction, critical phenomena, all these four topics are most important. So if you are thorough with one, two, three topics, this chapter is done. So if you are thorough with all these topics, this chapter is done. So it's very important chapter. Definitely you are going to get one or two questions for entrance exam. So please go through all these topics. That is summary of the chapter. And Boyle's law, Chance law, you have to refer only graphs, and Avogadro's law, ideal gas equation. From ideal gas equation, you may expect a numerical. Dalton's law also you may expect a numerical. Graham's law of diffusion also you may expect a numerical. So only the underlined words what we have done and important star marks. From these, if you work out more questions, at least 100 questions if you do, that will be perfection in that chapter. So please, from the entrance books, whatever entrance books we have, from these three topics, you go do at least 100 questions. 100 questions you have to do so that you will be mastering this topic and easily you can score the marks in the entrance examination. I hope this is helpful to you. So please go through it and follow strictly what we have discussed. And what are the models which I have said important, you do work out more number of models based on that. All are very important. So with this, I am closing this lecture. So thank you all. Thank you all.